Hi, now let's discuss a bit about the relation between depth, trainability and generalization, and let's try to understand a bit more why residual connections actually had such a big impact in allowing us to train deeper neural networks. So as a matter of fact, trainability, so how easy it is to train an architecture, a neural network architecture, depends on a lot of model choices. For instance, the architecture itself is of course a great factor. The optimizer is very important, the way we initialize our parameters, the way we choose our hyperparameters. So all these things can actually positively or negatively influence the way we can train our architecture. Of course, the big question is, why are residual connections so that good? You know, like what is so special about them? So a couple of years back, we had this great paper shown here, very interesting one, which basically attempted to visualize in 3 dimensions the loss surface, how it looks like for the neural networks, like how it looks for the optimizer to actually optimize a particular neural network loss surface. So this was the VGG network, 56 and 110 layers deep. So we observe a very highly non-convex surface, right? So with lots of valleys and lots of like hills and mountains, very steep descents. However, by adding skip connections, suddenly things become much smoother. The surface becomes much less rough. Now gradients are much more representative of where an actual real minimum is. It wouldn't like be sort of accidentally pointing to a direction that it could be leading to a better minimum or not, depending on the initialization. And of course, what is very important to say here is that these visualizations should be used with a grain of salt, because there is obviously a dramatic dimensionality reduction. So it's good as as insight, as some evidence, but it's not no proof. However, I highly encourage you to read the paper. It's very fair in the way it's written, so it gives you all the necessary. It delineates all the limitations of it. So let's see now, we're using the same tools, what is the effect of different factors of architectures? Well, the effect of depth, it seems that deeper architectures have more uneven and chaotic surfaces with many more minima. So when you have a ResNet of 20 layers, it looks like, a roughly okay, a reasonable bowl, like surface of bowl. When we go to 56 layers, then it becomes a bit more, let's say, uneven. With 110 layers, we start observing many more local minima. So we observe that as we go deeper and deeper, even with the residual connections, we do have a nice big local minimum, but there are also all sorts of other smaller ones that might make the life of the optimizer hard. Interestingly, when we remove skip connections, things are much more, let's say, violent. So NS here stands for no shortcut connections. We observe that for 20 layers, again, it's not too different, maybe a bit more chaotic, but not too different. However, with 56 layers and no shortcut connections, it's basically a soup of local optima, very elongated regions, very weird shapes, right? And with 110 layers, it's even worse. So probably the resolution of the picture here is not high enough to observe this. So the problem is that with this kind of fragmentations, you normally require very good initialization, so that your optimizer starts from a good point and then goes to the good local minimum. Now you may understand that in such complex spaces this might be quite hard. I think it is sort of reasonably easy to have this by making sure that we've got orthogonal matrices. We initialize our random weights to be orthogonal matrices, and that's relatively easy for fully connected layers, but for convolutional layers it's more complicated. Generally, a good initialization is very important without skip connections. Another interesting element here is that with deeper layers we observe lower and lower rates, right? So indeed depth does make a big difference, and we observe that flatter minima are associated with lower test error. So having flat, like converging to flat solutions, is actually a good thing to have. When we are going to wider architectures, the observations were actually very similar. So quite interestingly, width makes the ball of our loss surface even wider, even flatter, even smoother. So great for us. When we remove skip connections, here in the bottom row, we observe a worse type of optimization, like loss surface. It does get better though. So having wider architecture does help our optimizer. Now we could also use the same visualization technique to show the effect of the optimizer, with of course some certain things to keep in mind, which I'm not going to delve into right now. It's not it's out of the context of today's lecture, but in any case, what we can observe, like the conclusion we can obtain, is that weight decay encourages optimization trajectories perpendicular to the isocurves. So like here, so here's weight decay. However, when we set our weight decay, so our L2 normalization, to 0, then our trajectories are quite often parallel, or sort of parallel to the isocurves, which means that instead of going to the direction of the local minimum, we sort of maintain solutions that attain similar local minimum over a duration of time steps. And now to the million-dollar question: why is it that skip connections actually make things so nicer? Why do they make the loss landscape better? Why do they propagate the signal easier? So the best explanation, to my knowledge right now, or one of the better ones, is that if you actually take the gradient with skip connections for our input x, and you decompose it. So here this is your f, your nonlinearity, times so over so the partial derivative of the nonlinearity with respect to the input x, but then you have to also add the partial derivative of the input with respect to itself, right, because of the skip connection. Now, because of this extra term, our final gradient for our input x contains the term from the layer above, right, because backpropagation follows the reverse path, which means that the gradient from higher layers are sort of propagated, they are carried to the lower layers untouched, without any modification. So therefore there is no the problem of vanishing and exploding gradients becomes much less important, because strong gradients and good gradients are maintained. Therefore it means that our loss surface becomes friendlier, right? So our loss surface has gradients. So because the gradients are more consistent or stronger, it means that our loss surface has to be smoother, and this is why we saw this type of visualizations. Thank you.